Hi everyone, this is chapter 3, Simulation Principles. This chapter will include three sections. So this is section number 1, and this section will be presented in three pre-recorded videos. So this is the first part of the videos. So let's see where are we now on the course map. As you see here, we are done on the first two chapters. In chapter 1, we had the basic concepts and definitions in simulation. And in chapter 2, we have several examples that we implemented in Excel. So we had a Monte Carlo simulation and also this discrete event simulation examples that we formulated in Excel. But now in this chapter, in chapter 3, we are going to have the general principles of discrete event simulation models. I can say the first two chapters are somehow introduction to our course. I can say the main chapter of this course is going to be started right now in chapter 3. So in chapter 3, we'll learn the general principles. So by knowing that, we can actually formulate and describe any system, I mean any discrete event system, in terms of a discrete event simulation model. Okay. And then in chapters 4, 6, we will have statistical models and King theory, which are somehow background knowledge for service systems. And then in chapters 7 and 8, we'll have random number generation and random variable generation methods. And chapter 9, input data modeling. So these chapters together will form the main body that we use this knowledge to build a simulation model. Okay. So the section 1 of chapter 3 is about an introduction and an example about the bank teller simulation. Okay. So in this section, we will have the concepts in discrete event simulation. We had these concepts in chapter 1, so we are going to review these concepts here as well, just to be fresh to learn the principles of discrete event simulations. Okay, and the main body of any discrete event simulation is the event scheduling or time advanced algorithm. So we'll see how this algorithm works in DES. Okay, and at the end we'll have an example bank teller model, and we will simulate this example manually to see how the time advanced algorithm works. Okay. So what's the objective of this chapter? The objective of this chapter is having a common framework for the modeling of more complex systems using discrete event simulations. So we're going to have a framework in this chapter that we can apply that framework for any discrete event system in order to describe that system or model that system in terms of discrete event simulation. Okay, so this is the objective of this chapter. And as you know, a discrete event simulation, in short DES, is a system that modeled in terms of its state at each point in time or time epoch. So yeah, in DES, we will model the system's state in discrete time. So we are going to see that how the system's state changes over time, and here specifically in discrete point of times. Okay, and so in DES we'll have a simulation clock, and then we will advance this clock on time based on the time occurrence of the events, and in each time epoch that we are having an event, then we will see what will be the impact of that event on the system's state, and we'll actually formulate or model the impact of those events in system's state. Okay. As we saw in chapter 1, in order to study and analyze the systems, we may need to develop a model. Then a model can include structural, logical, and mathematical relationships, right? If the system is too simple and we can represent that model by just mathematical relationships, that's great, because we can solve that mathematical model analytically and we can obtain an optimal solution for that system, like linear programming models. Okay, but if the system is too complex and it's not actually possible to formulate that system in terms of just a pure mathematical model, then we may need to use logical and structural relationships and formulations in order to represent that system. Okay, the simulation model actually lies in these kind of system, these kind of models that we will actually use logical and structural and mathematical relationships in order to formulate a system in terms of a simulation model. So a simulation model actually will describe a system in terms of its state. So yeah, we are going to show in our model that how the system's state changes over time. Entities and their attributes, sets, processes, events, and activities and delays. So when we say that we are going to build a simulation model, we mean that we are going to describe that system in these terms: the system state and how it changes over time, the system's entities and their attributes, the sets, processes, the events, activities, and delays. Okay. The entity, any object or component in the system that requires explicit representation in the model is called entity. So entities usually arrive the system from the outside, and then they move around the system for a while, and after a while they take their service and then they will leave the system, right? So yeah, this is the general behavior for the entities. For example, a server in a bank system, for example, a customer again, or a machine, or parts, right? These are the examples for entities. Okay. The system state or state variables. Usually we define several variables in order to describe the system's state at any time. Then the collection of these variables will actually describe the system's state in different angles, right? So, for example, in the bank teller system, the number of customers in the system, right? The number of customers waiting in line. So collection of these two state variables will describe the system's state at any time. And usually in this course, we will consider the discrete systems. This means that the system's state will change in discrete point of times, not continuously. If so, then that system will be called continuous system, right? But in this course, the systems that we are considering for simulation are in the category of discrete systems, and because of that, this simulation approach is called discrete event simulation. Okay. And the attributes, if the entities have attributes that the value of those attributes will individualize each entity from the others, then in that case, we have to define the attributes. Okay. For example, the priority of a waiting customer. Yeah, as you know, in the emergency department of a hospital, the patients arriving at department will have different priorities regarding their situation, right? Or the routing of a job through a job shop, right? If we have a job shop and we have orders coming from the outside, then each order or a job may have different flow of operations, right? So again, here, since somehow the orders are individual, I mean, differentiated from the others, so we have to define these attributes, okay? So after defining the entities, the attributes, and the state variables, we may need to define the list or the sets. So, for example, in the bank teller system, if we are interested to know which customers are in the waiting line now, then we need to use the list or the set. So a list or set will be a collection of associated entities ordered in some logical fashion. So it could be permanently or temporarily, yeah. Or for example, the customers in waiting line ordered by priority or the service discipline, for example, first come, first serve, or first come, last serve, and so on, okay? So yeah, if we don't care about who waits now in the waiting line, then we don't need to define the list. But if we want to track the customers one by one or maybe individually and see which customers waited for how long in the waiting line, then we need to define the list or sets for our simulation model. Okay. The event. Okay, so after defining the entities, the attributes, the sets, all these ones are related to entities, right? Now it's time to define the events. Okay, so the event is an occurrence that changes the state of a system or a state variable. So yeah, I mean, an event is an occurrence that when it occurs, the system's state changes. Okay, for example, arrival in the bank teller system, arrival is an event, and when arrival happens, the system's state changes. So yeah, or departure, right? Customer departure, customer arrival, or in other systems, for example, failure, order arrival, task completion, right? And event notice. So this is again related to the event. So when we define the events, we need to define the event notice as well. So in the future event list, we will actually obtain the events by having an event notice for each event. And usually an event notice will include the type of the event. For example, it's arrival or departure, and the time of occurrence, for example, at 5 or at 3, for example, or maybe the entity, right? Which entity is related to this event. So yeah, usually an event notice will include these 3 data, and we will define event notice in future event list. Okay. Future event list, FEL, or event list. So this will be a list of event notices for future events, and these events will be ordered by the time of occurrence. For example, for the bank teller system, we may have this FEL. For example, as you see here, we have 2 events which mentions the first one is for the type of the event is departure, and it will be occurred at after 3 minutes, for example. Or the other event is arrival. I mean, the type of it is arrival, and it will be occur at after 5 minutes. So, and as you see here, we have ordered these two events in the FEL. Okay, and the activity actually is it's not actually an activity. It's just a duration of time. Okay, yeah. Here we don't mean actually a task or activity by having the concept of activity here. So it's just a duration of time of a specified length. Okay, and it will be assumed that we know the duration when it begins. So how we know that it could be a deterministic. So if we have a deterministic duration time, so we know it with certainty, or it could be based on a statistical distribution. Okay. For example, for the bank teller system, inter-arrival time, service time, or any other processing time will be considered as activity in the simulation model. Okay, and yeah, and usually the duration of activity is not affected by the occurrence of the events, unless we may have some logic in the system that the order of occurrence of the events maybe have impact on the duration. Okay. So the next concept here is a delay. Delay actually, again, it's a duration of time. Okay, but the difference between delay and activity is that the length of the delay is unspecified. Okay, so when it starts, we don't know when it's gonna be ended, right? So, for example, the customer's delay in a last in first out waiting line, right? So yeah, these are called as delays in a simulation model, but activities actually when it starts, for example, service time or inter-arrival time, we know that what will be its duration. Okay, and the clock here actually we assume a variable for simulation time, and we call it as clock. So in DES, usually we advance the clock by the time of the events in future event list. Okay. As a comparison between activity and delay, for the activity when it begins, we can calculate its duration, so its end will be obtained at that time. But for the delay, it's impossible to calculate its duration based on the input data. For example, if we consider the customer's delay waiting in line, so the delay or the waiting duration will depend on the number and service times of customers ahead, and also the availability of servers and equipment, right? And yeah, usually the delay's duration will be calculated during the simulation, and at the end we'll have it as part of the performance measures. Okay, so this was the first part of section 1 of chapter 3, and in the next two parts we will have actually the time advanced algorithm for discrete event simulations, and also an example for manual simulation. Okay, thank you.